All right, so we are first going to start looking at what we call trigonometric ratios, or shortened as trig ratios. So we are going to find the sine, cosine, and tangent of an acute angle. And then we're going to use our trig ratios to find the side lengths in a right triangle. So here's going to be what we call a new symbol. So this is theta. It is a Greek letter, and it is typically used to represent unknown angle measures. So as you kind of get higher into mathematics, your regular alphabet, A, B, C, D, E, F, G, all of that typically stands for side lengths, where your Greek letters, such as alpha or beta or theta, you have gamma, there's a whole bunch of other ones, but all of our Greek letters will typically stand for an angle measure. So A through Z stand for side lengths. Your Greek letters, which we're going to be using theta, will stand for angle measures. And you will see that again in pre-calc as well. All right, so when we're talking trig ratios, we are looking at a right triangle. And a trig ratio is the ratio of two sides in a right triangle. So what we say sine of theta is going to be the ratio of the opposite side compared to the hypotenuse. So what that means is if you're given a right triangle and you're given an angle, one of the acute angles, we'll do the one below, theta, the sine is going to be the ratio of the opposite side compared to the hypotenuse. So the side opposite of theta would be over here. And then the hypotenuse is always the same. It's across from that 90 degrees. So it will be over here. So the abbreviation for sine, you just take the E off and you have sine of theta, is going to be the ratio of the opposite compared to the hypotenuse. And then we're going to shorten that just a little bit more to say S is equal to O over H. Okay. Now our cosine, so again, if we're given a right triangle and we are given an angle theta, and it has to be one of the acute angles, our ratio for cosine is going to be the adjacent side compared to the hypotenuse. So in our diagram here, this would be our adjacent side, because it's the side that is next to the angle, over the hypotenuse, which again is still that same side that's across from 90. So we're going to shorten that a little bit. So cosine abbreviates to COS, but it is still pronounced cosine, would be our adjacent over our hypotenuse. And then we'll shorten again just a little bit more to say that it is C is equal to A over H. And these abbreviations over here will make a little bit more sense in a second. All right, and then finally our tangent. So again, in a right triangle, the tangent of an angle theta is going to be the ratio of the opposite compared to the adjacent. So we have tangent of theta is opposite. Sorry, apparently I can't spell today. Over then the adjacent. So to abbreviate that, so tangent goes and abbreviates to tan, but still pronounced tangent, is going to be that opposite over adjacent. And then T is equal to O over A. So an acronym to kind of help us remember our trig ratios comes from this. So we have SOH, so sine is opposite over hypotenuse, CAH, TOA. So you'll hear me often say, think of SOHCAHTOA. So that just tells us what each trig ratio is representing. It's just an acronym to help us. But remember, we are looking at the ratio of two sides of a right triangle. All right, so in trig, the letter of the vertex of the angle is often used to represent the measure of the angle. So when I say the sine of A, if I have a right triangle, ABC, the sine of A can be written as the sine A. But what it's talking about is it's the sine of angle A. But we just abbreviate it to which trig ratio we're using and then which angle we are using. All right, so now we want to go ahead and figure out these trig ratios. And then we're going to compare them. So what I always like to do is first I want to circle the angle that I'm working with. So for these first three on the left, we're working with angle J. So I'm going to circle my angle J, and let's label our opposite, adjacent, and hypotenuse. So the side that is opposite of J is going to be 60. The side adjacent to J would be 11. And then 61 is that hypotenuse. So when I am looking for the sine of J, I'm looking for the ratio of the opposite compared to the hypotenuse, which would be 60 over 61. And that's all that we're looking for. So the cosine of angle J compares your adjacent to your hypotenuse. So my cosine would be 11 over 61. And the only thing that you could potentially go further on is if either of these ratios simplify, but they do not. Okay, and then finally we need the tangent, which is going to be the opposite side compared to the adjacent. So I would have 60 over 11. So those are my three trig ratios for angle J. Now let's go ahead and look at angle K. So now, if we, let's start this over. So when we switch angles, look at what happens. So now I'm working from angle from angle K. So now what side is opposite of angle K? And now it is 11 is opposite. Okay, now what side is adjacent? Well, that would be the 60. But notice that the hypotenuse stays the same. All right, so now what I want you to do is pause the video and see if you can write the trig ratios, sine, cosine, and tangent for angle K. All right, let's go ahead and see how we did. So sine is the ratio of the opposite side compared to the hypotenuse. So that would be 11 over 61, because we're taking that opposite over the hypotenuse. Okay, the cosine of angle K compares the adjacent to the hypotenuse. So that would give us the ratio of 60 to 61. And then finally, the tangent compares the opposite over the adjacent. So we have 11 over 60. So now let's go ahead and compare. If you look at the sine of J and cosine of K, those are the same, which would make sense because what happens when I switch angles is the opposite and adjacent sides switch. Okay, likewise with the cosine of J and sine of K, those are also the same since the opposite and adjacent sides switch. And then finally the tangent, those are reciprocals of each other. Because again, the opposite and adjacent sides switch when we switch the angles. All right, so now we need to go ahead and talk about using a calculator. So to use a calculator to find our trig ratios, all we're doing is punching this into our calculator. What you need to remember though is that you are in degree mode. There is also a mode called radians. Do not be in radian mode, otherwise you will get all of these wrong and be very, very confused. So, what you typically look for on your calculator is the abbreviation DEG. That will stand for degree, whereas RAD will stand for the radians. And again, we don't want radians. All right, so now we want to go ahead and punch these into our calculator and figure out the answer. So I will show you how to do it on the Desmos Scientific Calculator. If you have a TI-30, those are also really good to use. But I will show you on Desmos. So when we type in the sine of 52, we get 0.788, and we're rounding to the 100th. So then my 8 would round up to 0.79. Okay, and then on our next one, I'm looking for the cosine of 19. So we punch that into our calculator, and we get 0.945, which would then round up to 0.95. All right, for the next few examples, we actually want to put all this information into practice by finding side lengths. So we want to go ahead and find the length of BC to the nearest hundredth. So now we know we can use Pythagorean theorem, 45, 45, 90s, or 30, 60, 90 triangles to find side lengths. But let's look at what we know. This is not a special right triangle because the angle is 23. And I only know one side. So the reason we need to know trig is so that we can figure out these side lengths without being able to use either Pythagorean theorem or our special rights. So we want to find BC, so we're going to go ahead and call that side length x. Now we're going to circle the angle that we know. So I know angle A. So now we want to go ahead and label the sides that we know. So I want to find BC, which is the side opposite of our angle. And I know the side length AC, which is 4, and I know that is our hypotenuse. So right away, I know I'm using the opposite over the hypotenuse, which is sine. So I say the sine of our angle measure, which is 23, is equal to our opposite side, which is x, over our hypotenuse, which is 4. So what we get is an equation that we can now solve for x. So to get x by itself, I would multiply by 4 on both sides. So we get x is equal to 4 sine of 23. And now this is what we can go ahead and put into the calculator. So we would get our final answer out. So we get that x is approximately 1.56, and then we have inches. All right. So now on the second example, we're looking for QR. So I'm going to call QR our side x. And again, I'm going to circle the angle that we know. So we know this angle P. And now we can go ahead and list our sides. So the side that we're trying to find, x, that side is opposite. And the side we know, PQ, is adjacent. So now we need to think of what ratio uses the opposite and the adjacent, and that would be tangent. So to set up our equation, we say the tangent of our angle measure 50 is equal to our opposite x over our adjacent, which is 8.1. Now we have an equation that we can solve for x. So we can multiply by 8.1 on both sides. So we get x is equal to 8.1 times the tangent of 50. And now this is what we can go ahead and put into our calculator. So we get that x is approximately 9.65 meters. And then that is our side length, so QR is equal to my 9.65 meters. And there we go. All right, so on our last example, we're finding both AB and we're finding BC. So we're just going to start by finding AB. So we're going to call AB X. So we know angle B, so I'm going to circle angle B, and now we can label. So AC is the opposite, and AB is the hypotenuse. So I'm able to set up my trig ratio. So what uses opposite and hypotenuse? That would be sine. So I can say the sine of 15 is equal to our opposite, 10.2, over our hypotenuse, which is x. So now x is in the denominator, but we're going to solve very similarly. So I would multiply x out of the denominator on both sides. So we then get x times sine of 15 is equal to 10.2, since the x's cancel. But this is not quite solved for x yet. We need to go ahead and divide both sides by the sine of 15. Okay, so we get the sine of 15s to cancel on the left-hand side, so we know that x is equal to 10.2 divided by the sine of 15. And now this is what we can put into the calculator. So we get that x is approximately 39.41 feet. And that's our AB. So now we also want to go ahead and find BC. So I'm going to call BC Y, and this is the adjacent side. So now I have the opposite and the adjacent. So to find BC, I can say we're using opposite and adjacent, so the tangent of 15 is equal to our opposite side, 10.2, over our adjacent side, which is y. And now we can do the same process as we did to find AB. We can multiply y out of the denominator, so we have y times the tangent of 15 is equal to 10.2. And now we can go ahead and divide by the tangent of 15. And we get that y is equal to 10.2 divided by tangent of 15. And now this is what we can put into our calculator. So we get that y, which is CB, is approximately 38.07 feet. All right. So that does take care of everything in section 8.2. Please let me know what questions you have. And if you do need help using your calculator, please reach out to me. I'm more than happy to show you on any type of calculator that you have. Otherwise, have a great day. We'll see you next time.